Every bulldozer working today, from the smallest landscaping machine to the 200-ton monsters reshaping mountains in Australian coal mines, traces its design back to a single innovation made in 1904. Not the blade, not the hydraulics, not the engine, the tracks. Benjamin Holt's track-type tractor, built to cross California peat fields without sinking, established the mechanical foundation every bulldozer still uses. But the machine we call a bulldozer didn't exist in 1904. Holt built a tractor. The transformation from farm tractor to earth-moving weapon took 2 decades of incremental innovation, a world war that proved its value, and another war that made it indispensable. This is the complete history of the bulldozer, how it evolved from agricultural experiment to the machine that built modern civilization, then how it went from 5 tons to 152 tons, how it became so essential that Japanese forces in World War II called it the American secret weapon, and how a machine designed to push dirt became accurate to within 1 inch using GPS satellites. November 24, 1904, Stockton, California. Benjamin Holt tests his first track-type tractor. Wooden slats mounted on continuous belts replace traditional wheels. The physics are elegant. Distribute weight across 40 feet of track instead of concentrating it on wheel contact patches. Ground pressure drops to 1/5 of wheeled tractors. The machine crosses soft peat soil that swallows everything else. Holt patents the design and starts selling track-type tractors to farmers, loggers, and mining operations. But these are tractors, not bulldozers. They pull equipment, plows, harrows, scrapers, timber sleds. The track system solves traction and flotation problems, but the machines don't push earth. They don't grade, they don't clear, not yet. The blade comes later, and the origin is surprisingly unclear. Multiple manufacturers experimenting independently in the early 1920s. Farmers and contractors realized that attaching a simple steel blade to the front of a track-type tractor creates something new. A machine that can push material instead of just pulling it. Early blades are crude, flat steel plates welded to angle iron frames, fixed position, no hydraulics, adjusted by hand with block and tackle between passes. But even crude blades prove immediately useful. Clearing stumps, pushing dirt, grading rough roads. The concept spreads quickly across the construction and agriculture industries. The name bulldozer emerges from this era, and though the exact origin remains debated, the most credible theory suggests bulldoze, meaning a large dose of force, a bull-strong dose of pushing power. By the late 1920s, the term bulldozer is common industry language. The machine has separated from its tractor origins into something distinct. The 1930s established the bulldozer as essential equipment. Caterpillar, formed from the 1925 merger of Holt and Best companies, introduces the D2 through D8 series. Each number represents increasing size and power. The D2 for small jobs, the D8 for heavy construction. These machines feature improvements over the experimental 1920s designs. Cable-operated blade control allowing the operator to raise and lower from the seat. Stronger frames to handle pushing loads. More powerful engines. But they are still mechanically simple. Direct drive transmissions. Manually shifted gears. No power steering. Operating a 1930s bulldozer requires physical strength and constant attention. The Great Depression paradoxically helps establish the bulldozer's importance. New Deal infrastructure projects, the Civilian Conservation Corps building roads and dams across America. Bulldozers prove faster and cheaper than horse teams and manual labor for earth moving. The machines that might have seemed like expensive luxuries become practical necessities. Then comes December 1941, Pearl Harbor. The United States enters World War II, and the bulldozer enters military history. The Navy's construction battalions, the CBs, deploy across the Pacific with Caterpillar bulldozers as their primary tool. The mission is straightforward, but brutally difficult. They'll follow the Marines onto contested islands and build airfields under fire. The timeline is impossibly tight. Bomber and fighter operations require prepared runways. Islands need functioning airstrips within 48 hours of initial landing, sometimes faster. The bulldozer makes it possible. CB operators work around the clock, clearing jungle, grading coral, compacting surfaces, building revetments. The machines operate in tropical heat that breaks equipment designed for temperate climates. Saltwater spray corrodes every exposed metal surface. Operators work under artillery fire and aerial bombing. Maintenance happens in the field with whatever parts supply ships deliver. The bulldozers keep running because stopping means aircraft can't land and the entire invasion stalls. Japanese forces recognize the bulldozer's strategic importance early. Intelligence reports from Pacific Island battles repeatedly mention American earth-moving capability as a critical advantage. Some accounts claim Japanese commanders called bulldozers the American secret weapon, though this specific phrase is difficult to verify in primary sources. What's documented is their impact. Islands that would take weeks to prepare using manual labor become operational airfields in days with bulldozers. The speed of American airfield construction directly contributes to the island-hopping campaign's success. Each captured island becomes a bomber base projecting power further into Japanese-held territory. The bulldozer isn't glamorous like fighters and battleships, but it's equally essential. The machines that build the runways enable the aircraft that win the air war. World War II also drives rapid bulldozer development. Armor kits to protect operators from small arms fire and shrapnel, stronger blades to handle obstacles like concrete fortifications and fallen trees, improved track designs for better flotation in sand and mud, angle dozer and tilt dozer blade configurations for specialized work. By 1945, military dozers are substantially more capable than their 1941 predecessors. That wartime development feeds directly into post-war civilian markets. The interstate highway system, authorized in 1956, creates demand that dwarfs even wartime production. 41,000 miles of divided highway requiring earth moving on a scale never attempted, cuts through mountains, fills across valleys, grade specifications measured in fractions of a percent across hundreds of miles. In 1955, a Honda Caterpillar introduces the machine that will define interstate construction, the D9 bulldozer. The D9 represents a massive increase in capability over earlier dozers. More horsepower, wider blade, heavier operating weight for better traction. The D9 can move more material per hour than smaller machines, and on a project measured in thousands of miles, that productivity difference matters enormously. If you worked interstate construction in the 50s, 60s, and 70s, you worked with D9s. The machine becomes synonymous with heavy earth moving the same way Caterpillar becomes synonymous with tracked equipment. But Caterpillar's dominance doesn't go unchallenged. Japanese manufacturer Komatsu, rebuilding after World War II, enters the bulldozer market with a strategy focused on matching Caterpillar quality while undercutting price. Through the 1960s and 70s, Komatsu grows from regional player to global competitor. Their machines prove reliable. Their prices run 20 to 30% below comparable Caterpillar models. The competitive pressure forces innovation across the industry. Hydraulic blade control replaces cable systems, giving operators precise control and faster cycle times. Torque converters and power shift transmissions replace manual shifting, reducing operator fatigue and improving productivity. Enclosed, climate-controlled cabs replace open operator stations, making the machines tolerable in extreme heat and cold. Each improvement raises the baseline for what customers expect. The technology race produces increasingly specialized machines, swamp dozers with extra-wide tracks for minimal ground pressure, working in wetlands and soft soils where standard dozers sink. Coal dozers with sealed cabs and filtered air systems, protecting operators from coal dust in open pit mines. Low ground pressure dozers for pipeline work across tundra. Each variation optimizes the basic bulldozer design for specific applications. The military develops its own specialized variants. The Caterpillar D9R armored bulldozer used by Israeli Defense Forces and U.S. combat engineers. 15 tons of armor protecting the operator and critical components. Designed to operate under fire, clearing roadside bombs and obstacles in combat zones. The armored D9 demonstrates how far bulldozer design has evolved from agricultural tractors. This is purpose-built military equipment. The 1970s bring the largest bulldozer ever built, the Komatsu D575A. EDOF specifications that stagger even by modern standards. 152 tons operating weight, 1,150 horsepower, blade capacity of 69 cubic yards in a single pass. The D575A is built for a specific application. Japanese coal mining operations moving overburden at massive scale. The economics only work at the largest mines where productivity per operator hour justifies the machine's enormous capital cost. Caterpillar responds with the D11, introduced in 1986. Smaller than the D575A, but still immense. 105 tons, 850 horsepower, 45 cubic yard blade. The D11 becomes Caterpillar's largest production dozer, a title it still holds. Current D11T models cost over $2 million. The size comparison to 1904 origins is almost absurd. Benjamin Holt's first track-type tractor weighed about 5 tons. A modern D11 weighs 21 times more and produces roughly 170 times the horsepower. But the most significant evolution isn't size, it's control systems. Through the 1990s and 2000s, bulldozers integrate electronics and GPS guidance that transform how they work. Early systems simply display position and blade elevation to the operator. Later systems provide slope guidance, helping operators maintain precise grades without constant surveying. The current generation goes further. Fully automated grade control. The operator drives the dozer along the work area. The GPS system, receiving corrections from base stations to achieve accuracy within 1 inch, automatically adjusts blade height to match the programmed surface elevation. The dozer cuts high spots and fills low spots automatically. The operator steers and monitors, but doesn't manually control blade position. The productivity and accuracy gains are substantial. Survey crews that might have staked grade every 50 feet can now program an entire site surface into the GPS system. Dozers work to final grade without intermediate survey checks. Material is moved once instead of multiple rough and finish passes. Automated systems also reduce operator skill requirements for basic grading work. A veteran operator with decades of experience can still outperform GPS on complex work, reading the material and adjusting technique instinctively. But for straightforward grading to a known elevation, GPS allows less experienced operators to achieve results that once required years of skill development. The technology doesn't replace operator expertise entirely. It raises the baseline and makes good operators more productive. Modern bulldozers also incorporate telematics and remote diagnostics. Each machine reports its location, hours, fuel consumption, and system health to central servers. Fleet managers monitor dozens of machines from office computers. Maintenance is scheduled based on actual operating hours and conditions rather than fixed intervals. Diagnostic codes alert mechanics to problems before catastrophic failures occur. Some manufacturers offer remote support where technicians can access machine data and troubleshoot issues without traveling to the job site. The connectivity transforms bulldozers from isolated machines into networked assets, generating continuous data streams. The engineering debates that defined earlier eras haven't disappeared. So high drive versus low drive track configuration still generates strong opinions among operators and engineers. High drive places the final drive and sprocket at the top of the track frame, keeping them out of dirt and debris. Proponents argue for reduced wear and easier maintenance. Low drive places the sprocket at ground level, providing better protection inside the track frame. Advocates argue for more stable operation and less shock loading. Caterpillar uses high drive. Komatsu uses low drive. Both systems work. The debate continues. Blade design remains an active development area. Straight blades for general work. U-blades with curved wings for maximum capacity. S-blades with aggressive curves for ripping and heavy pushing. Semi-U blades balancing capacity and versatility. Coal blades designed for minimal spillage. Each configuration optimizes for specific materials and applications. Modern blades incorporate wear-resistant alloys and replaceable cutting edges, extending service life in abrasive materials. Track design has evolved from simple metal plates to sophisticated engineered systems. Sealed and lubricated track systems reduce maintenance. Rubber pads on track shoes reduce noise and surface damage for work on paved roads. Track tension monitoring systems alert operators to improper adjustment. Each improvement extends component life and reduces operating costs. The fundamental design established in 1904 remains unchanged. Tracks distribute weight. An engine provides power. A transmission converts that power to the tracks. A blade attached to the front pushes material. Everything else is refinement of those core principles. You can trace a direct line from Benjamin Holt's wooden slat tracks to the sealed, greased track systems on a modern D11. The basic physics haven't changed. The engineering has just gotten dramatically better. Looking forward, the next evolution is already visible. Autonomous and semi-autonomous dozers operating without human presence. Caterpillar and Komatsu both field autonomous dozers in mining operations. The machines execute programmed patterns, moving material without operators. Safety improves by removing humans from hazardous environments. Productivity can run 24 hours without shift changes. The technology works in controlled environments like mines with detailed mapping and limited variables. Expanding autonomous operation to general construction presents harder challenges. Construction sites change constantly. Obstacles appear, and other equipment moves unpredictably. Human workers are present. Full autonomy in uncontrolled environments remains years away, but the trajectory is clear. Electric drive systems may replace mechanical transmissions in the next decade. Electric motors provide precise control and eliminate complex power shift transmissions. Battery technology for machines this large remains challenging, but hybrid systems combining diesel generators with electric drive motors are feasible now. Fuel efficiency and emissions requirements will likely drive adoption. The bulldozer's fundamental role won't change, moving earth efficiently, clearing obstacles, grading surfaces, building roads, mines, foundations, and all the prepared ground modern civilization requires. The machines will get smarter, more efficient, more automated, but they'll still be doing what they've done since the 1920s, pushing dirt with tracks instead of wheels. Every bulldozer on Earth is based on a design from 1904 because that design solved the fundamental problem perfectly. Everything since has been making it better at the job Benjamin Holt's innovation made possible. The tracks still crawl, the blade still pushes, the bulldozer still builds the world.